All right, so let's continue with our discussion here. Okay, so we have essentially a first order model, but the input is delayed by theta p. Okay, so the model parameters that we have, clearly three of them. Okay, we have process gain that we need to find, tau p, which is the process time constant, and also we have theta p, which is the process dead time, so-called process dead time. So the time delay inherent in the system. Okay, so if we think about what kind of a normally an overdamped process, okay, so let's say if this was, let's say if this is our reference, and let's say this is the steady state value of the output, so this is YSS, this is our reference R of t. So normally the process would be like it's coming here, and then the process, a second order process, right, will exhibit a response like this. Okay, so this is an overdamped second order response. In fact, it can be a higher order system, but with a dominant second order response. Okay, so what is so the idea is to fit to this higher order system a simplified first order plus dead time model. Okay, so what first order model would look like? Remember, a first order model would have a response that is immediately starting to rise. So a manual fit to this would be something like this, right? So, okay, so you see there is here a pure delay, and then a first order response. So the overall thing is first order plus dead time response. Okay, so the idea is to represent a higher order response, overdamped response, by a combination of a pure time delay and a first order response. Okay, any ideas or comments or questions here related with everything that we have discussed? Any questions? Okay, so in this context, one we call controller tuning, which is nothing but controller design, is basically nothing but defined as plugging process model parameters into pre-derived design formulas that can give us good performing controllers, right? Good performing PI, PID controllers. Okay. Our focus right now is still on self-regulating or non-integrating self-regulating processes. Okay, so we are basically discussing processes that if you apply a step response, if you apply a step input, you will observe a response that's going to converge into a steady state value. Okay? So our next thing that we need to discuss is, okay, now we have a system model, first order plus dead time. How can I actually perform system identification using this model? Okay, system identification using this FOPDT model. So what is around, obviously, around an operating point? Okay. So what you do is you apply to the system at a given time, you come in with a bias term, so a constant input, and you so-called bump the process. Okay, so this is U bias plus some delta U. Okay, so this is known as bump the process. So this is my input, okay, U of t. So you come in with a bias signal that you have determined as your operating point, and you suddenly introduce a step input on top of that bias point, and that's going to give you a response, obviously. Okay, so the plant will respond by having a steady state value initially at the operating point. So let's call this, for example, Y operating points. Let's say this is our YOP. So this is Y of t. So what will happen is that the system will give you a response that's gonna converge to YOP plus some delta Y. Okay, so the system response would be something like it's going to come in here. As soon as you apply the input, the system will respond and it will converge to a new value. Okay, so what we are trying to do, again, I repeat, is to identify this response in terms of first a delay, and then essentially a first order response that becomes converging to okay, so this we will identify as our delay, and also we will identify a time constant. Okay, so we need to find out our process gain, the process time constant, and the process dead time or time delay. Okay, so these are very reasonable models for even higher order, for let's say some higher order process models. Okay, that's the popularity of the of the FOP DT model. Okay, so how do we how do we find the time delay and the time constant and the process gain? Okay, so let's call this experimental determination. So experimental determination of FOPDT model. Okay. So basically there are many sources that discuss this, but it's relatively simple. Okay, so you have a response yt, you have a steady state value of the output yss, and you start with an operating point yop. Okay. So here is your response. Okay. Now, first of all, the process gain is very simple to calculate. Okay, it's simply the ratio of how much the output has moved in response to how much the input has moved. Okay, so that's the gain, the difference in y. So this magnitude over here is your delta y. Okay, and you know how much your delta u has moved. So this gives you the process gain. One way cited in the literature for finding out about the process time constant is that you find first the time where the output reaches. You divide this into basically 1/3 of delta y and 2/3 of delta y, and you find the times corresponding to those instants. So let's call these T13 and also T23. Okay, and one approach in the literature is that the time constant of the process is given by this formula, is that you just find the time difference between the 2/3 and the 1/3, and then you divide that by 0.7, and that gives you the process time constant. Okay, and similarly from the same measurements, the time delay is measured by T1 1/3 minus 0.4 tau p. Okay, so that's so one way of computing FOPDT parameters.
Hocam bir şey sorabilir miyim?
Yes.
1/3 delta y dediğimiz orijinden itibaren mi, YOP'den itibaren mi?
Orijinden itibaren diye bir kavram yok burada. Her şey operating point etrafında.
YOP artı 1/3 delta y.
Delta y YOP ile equals YSS minus YOP. Dolayısıyla orijinle hiç alakanız kalmıyor artık. Nereden başladıysanız. Tamam?
Tamam hocam, sağ olun.
Bu arada literatürde so there is another way of calculating time constant in the literature as well, which is equally valid, okay? Is that people actually calculate the points which is about maybe 63% of delta y, okay, and another way which is also valid is to calculate tau p as approximately um, let's say time it takes to reach 63% of delta y. Okay, so it is, if this is your 63% of delta y, okay, so that is a time here which we can call t 63%. Okay, so we have tau p approximately equal to t 63%. Okay.
Hocam,
Just give me a second.
Laboratuvar. Tamamdır.
Buyurun, söyleyin.
Sorayım mı? Tamamdır.
Laboratuvarınız
laboratuvar
12.30'da sanıyorum.
Benim baktığım... presini yaparken ben bakmıştım FOBDT'ye de. Orada internette bulduğum bir örnekte bu %63 ile dead time arasındaki mesafeyi tavsiye olarak alıyordu. Bundan çok daha farklı bir sonuç vermez mi o? Hatalı mıymış hocam?
Sorry. Tamamen haklısınız. Time it takes to reach from the start of a clear response. Teşekkür ediyorum düzeltme için. Şöyle olmuş oluyor. While theta p time to see şöyle diyelim, time from the step to see a clear response. Buradaki tabii ki bu alternatifin bir sıkıntısı şu: tamamen sübjektif bir şeye dayanıyor. Yani time delay için siz hani şurada, hani şu ne demek, hani time to from the step to see a clear response. Yani response'a bakıyorsunuz ve hani response'un harekete geçtiğini düşündüğünüz anı delay olarak işaretliyorsunuz. Yani şöyle bakarsanız mesela, gene bir şey çizelim. Hani şöyle bir S-curve görüyorsunuz. Şimdi buraya bakıyorsunuz, hani diyorsunuz ki işte şurası olsun, ben şurayı theta p olarak işaretliyorum. Niye? İşte daha öncesinde pek bir sıfırdan farklı bir şey göremiyorum. Hani approximate theta p demiş oluyorsunuz. Bayağı sübjektif yani öbürüne göre. Ama ikisi de kullanılıyor. Yani şuradaki de bizim referans kitaplarımızdan birinde verilen ifade. Şu daha önce kutu içine aldığım. Ama bunu da kutu içine alıyorum. İkisini de kullanabilirsiniz. Sonuçta unutmayın, bunların hepsi tamamen approximate bir takım modeller. Kusura bakmayın, figürüm biraz geç geldi. Evet, soru var mı? Figür bu arada gidiyor geliyor falan filan. Bir saniye. Şöyle yapalım. Söyleyin.
Benim sesim size ulaşıyor mu?
Ulaşıyor, dinliyorum.
Sizin önerdiğiniz sitede App Monitör'de işte YouTube'da bunu anlatırken işte ben Pre için baktığımda yine görmüştüm. Dead time'ı da şöyle bulduruyordu. O yükseliş kısmına bir tangent line çizip onun operating point'i kestiği, yani daha doğrusu y is equal to YOP'yi kestiği noktayı dead time olarak kabul ediyordu.
Evet.
Ben şimdi mesela laboratuvarda öyle yaptım. Sınavda falan onu kullansam yani sonuç doğru kabul edilir mi, yoksa ilk verdiğiniz modeli mi kullanmak gerekir?
Yani şöyle, buna yönelik bir nümerik bir soru zaten sormam. Dolayısıyla hani bunlardan herhangi birini kullanabilirsiniz. Yanına bir justification yazdığınız sürece hiçbir sıkıntı olmaz. Yani bu sonuçta theta p'nin bulunması için birkaç tane yöntem var. Bir tanesi dediğiniz gibi işte bu tanjantın x eksenini kestiği nokta olarak, tabi burada kötü çizdim. Çünkü tanjant aslında şeyden ayrılmıyor. Yani bu şekilde bir ayrılma olmuyor. Tam o düz noktasını hani tanjant olarak alıyorsunuz. Bu kullanılabilir. İşte response'a baktığınızda gerçekten non-zero bir response gördüğünüz ilk an olarak alınabilir. Veya yukarıda verdiğim formülden hesaplanabilir. Bence hepsi kullanılabilir diye düşünüyorum.
Tamamdır, teşekkürler.
Bu hakikaten bu controlguru.com, işte apmonitor.com'da size verdiğim ders linklerine bakmak çok faydalı olur diye düşünüyorum. Çünkü orada da güzel bir anlatım bununla ilgili var. Şimdi let's continue. I'm going to erase this part. So how do we use this model? Okay, once we obtain this model, so this is from actually controlguru.com, you know, that's instructor that I have recommended to you. So he gives this as the open loop reaction curve design procedure. And it's given as a procedure, but essentially it's based on this bump test and the obtained FOPDT model and some design formulas, okay? And later on I will derive these design formulas for you in the following lectures, but for the time being, let's assume that the design formulas are already available. Assume design rules are available for now. Okay? So the procedure is as follows. You establish an operating point. Establish an operating point. Sometimes it's called a design level of operation, level of OP. Okay? The second is that you bump, which is kind of the jargon. You bump the process, meaning that you apply a step input around the operating point. And collect response data. You know, actually I would again want to emphasize response data from wire out to wire in. Okay? I mean, this is to emphasize that if you're controlling a process that is at the end of a communication line, you cannot simply go there and excite the system and collect the data over there. You need to collect the response data from the point that the controller is actually seeing the plant. That means you need to take into account the effects of the communication line to the plant, the communication line from the plant, and so on and so forth. Okay? Step 3, approximate the process. Approximate the process with an FOPDT dt model. So you obtain the model parameters. So the fourth step, which is kind of new now, is that you need to choose a desired closed loop time constant. A desired closed loop time constant. Let's call this tau c. Okay. Now this is important because this specifies what you want the system to do. Okay. This is another design parameter. Apart from the plant model, you need to tell the design what you want the overall system to do in terms of its time constant. In this design procedure, there is only one parameter for that, and it is how fast you want the system to behave after the controller is added. Okay? So the fifth step is use the model parameters together with chosen tau c in the design formulas to obtain parameters of the chosen, that means P, PI, PID, whatever, etc. Controller. So that means the choice of the controller is also up to you. What type of controller you want is also up to you. Okay? So we will see how we derive these design formulas, but these are so-called integral of time-weighted absolute error, eta A, formulas for the P controller. And also we have internal model control, IMC, internal model control derived formulas for PI and PID controllers. In the PID case, okay, you are talking about dependent ideal PID form, and also formulas are given for dependent ideal PID plus controller output filter. This filter is for the noise that we had talked about, which is because of the derivative term. So these design formulas also give you parameters for what kind of a cutoff frequency you can have for that low pass filter. Okay? So I'm gonna wrap up by giving you these design formulas, which will kind of be out of nowhere for now. But as I said, it's my promise that I'm going to derive all of these formulas for you in the coming lectures. Okay? So here are the design formulas. So given the plant parameters Kp, tau p, and theta p, and closed loop closed loop time constant. This is your design, right? Your choice, design choice. Let's call this tau c, which is the speed of the overall closed loop system. I'm gonna try to put the table over here. So we have basically we will have the gain Kc. We will have the integral time constant. This is known as the reset time in the literature. Okay, reset time, tau I, the integral time constant, derivative time, tau d, and also we have filter time constant. Filter time constant, and let's call this tau f. Okay, so these are our design parameters that sorry, this is giving me a hard time. So we will have formulas for all of these, and we will have this for also the different cases of a PI controller. And I will also give you later formulas for the P controller, but for the time being, a PI controller, a dependent ideal PID, DI PID, a set of formulas for that, and also dependent ideal PID, PID with CO filter, controller output filter. Okay? So in the case of PI, we will have 1 over Kp tau P over theta P plus tau C as your gain, and you will get tau P as your integral time constant. You don't have anything for the other two. Then we have 1 over Kp. Over here we have tau P plus 0.5 theta P over tau C plus 0.5 theta P in the denominator. And also the integral time constant is tau P plus 0.5 theta P, and the derivative time constant is given by tau P theta P over 2 tau P plus theta P. Nothing here. And finally, in the last case, we also have a specification for the filter as well. So I have here 1 over Kp. Again, in the numerator, tau P plus 0.5 theta P over tau C plus theta P, in this case, without the 0.5, tau P plus 0.5 theta P. Here, tau P theta P over 2 tau P plus theta P, the same. And also we have a control, filter time constant, and that's going to be tau C, tau P plus 0.5 theta P over tau P, tau C plus theta P. And all of this multiplies, sorry about the squeezed, times tau D. Okay? And I have this I have tau F the filter time constant is equal to alpha times tau d. So this is your alpha. Okay, so tau d is our derivative time constant. Okay, so alpha times tau d gives us the filter cutoff. So that's what we have, right? Now, so, you know, obviously, this requires for you to specify a desired time constant for the overall system. So I'm going to also discuss how to select tau c. Okay. So this closed loop time constant tau c determines the speed of the controller. Okay, determines the speed or the aggressiveness of the controller. Okay, so some guidelines are given for that. Okay, if you want aggressive performance, fast response, you can select tau c as the maximum of 0.1 tau p and 0.8 theta p. So you see that this is like selected as 10 times faster than, almost 10 times faster than the plant itself, if you want an aggressive performance. Okay, and there is a very simple relationship between the subsequent ones. If you can call a moderate performance, tau c is selected as the maximum of simply tau p and 8 theta p. So you see that there is maybe 10 times difference between the two. And if you want a conservative performance, you can select a maximum of 10 tau p and 80 theta p. Okay, again, the same kind of 10 times difference here. All right, so you might argue, what's the point of having a controller if I'm not speeding up the system? But remember that your objective might be actually to stabilize the system. So if the original system has a time constant tau p, maybe it's too close to the stability boundary. So you may actually even want to slow down the system by the controller to make it more stable. Okay, so conservative performance is like you slow down the system, which with 10 times the time constant, so that you have even more stable system. As a final note, I want to finish by discussing this controller output filter. So another note, the CO filter is to filter the high frequency noise, is to filter the high frequency noise introduced or amplified by the derivative action which causes some kind of a chatter in U of t. Okay, before you actually supply it to the final control element, the actuator, so that you don't damage the actuator or lead into some kind of a operational problem. Okay, so here we have our system looking like this. So you have your PID controller here. You have your filter, and I'm going to just define the transfer function of the filter as well. So let me actually call this the CO filter. Then you derive, so you had U of t here, so you have U star of t here, final control element, final control elements. You can call this the actuator as well. So you derive the process. So, and you measure the response. Okay, so you have sensor and transmitter, sensor and transmitter. Over here, coming from the output y of t. Okay, so what is this filter? This is a first order low pass filter, a first order low pass filter with the given time constant, right? With TF time constant. Okay, so we have in the differential equation version df d over dt u of t, u star of t plus u star of t is equal to u of t. And as a transfer function, tau of s plus 1 u star of s is equal to u of s. So it's a very simple first order system with u star of s over u of s simply given by that first order transfer function. Okay? All right. So any questions so far? Up next is that we will try to really try to derive these design formulas from first principles. We will basically assume a certain linear approximation for the time delay and then use that in order to obtain our PID design formulas. But in order to do that, we will have to do quite a bit of work, including a concept called direct synthesis. Okay, so up next is direct synthesis, and later we will go to internal model control, and we will go to design formulas. Arkadaşlar